All right, we got the recording going. Okay, so I hope you guys have been checking your email because I've been pretty active this morning, working for you. You know, I work for you guys, and so I'm trying to do a good job. I sent out some presentations. I sent out the solution to the first Psych homework, and it's actually 2 emails. I remembered another presentation on the Desiccant stuff, and so I stuck that on a follow-up email. So hopefully you found all of those, because we have just a little bit to do in Psychrometrics today, and then we will move on to those other topics. Okay, so let me see here. Get myself. Let's see. Yep. Okay. So this is our last topic in Psychrometrics. So you can tell this note page is not quite as old as the other one. It's not yellowed. Actually, they're yellowed because they're engineering paper, but this is just a white piece of paper. But anyway, so evaporative cooling. And so this is something that we've kind of hinted around at, but we really haven't discussed, the topic directly. In the southwestern part of the U.S. primarily, and other areas you might see this. Typically areas that is pretty dry. We can create air conditioning by evaporative cooling, which means that all we need is a water source, a little pump, and a fan, and an enclosure, and some sort of a cheesecloth or some sort of a membrane that we can keep wet, pass air through so that the water evaporates. And that evaporation process brings on enough cooling that we can actually cool a house. And it's so dry in the Southwest that they want the water vapor in the air as much as they want the cooling. So it's a double win-win situation. Now, unfortunately, when you get up to the eastern part of the U.S., the humidity is such and the moisture in the air is such that they don't work very well, because the air coming in is not dry enough, and there's not enough potential to evaporate water vapor because the water vapor is already in the air, and so they don't work very well. So you don't see it too much. Sometimes in kitchens, poor people that work in kitchens in the southeast in the summertime, sometimes the building owner or whoever owns the restaurant is too cheap to buy real air conditioning, and so they'll put in a swamp cooler. Well, you get a little bit of benefit, but of course you're throwing additional moisture in the space, and there's already a lot of moisture in a kitchen, so they don't really work very well. But I have seen applications where people have put swamp coolers in kitchens just because they didn't want to pay for the equipment and they didn't want to pay the energy bill to run the actual air conditioning. But in the Southwest, a lot of houses are built without, compressors and regular refrigeration, air conditioning type systems. And the only cooling they have would be a swamp cooler or an evaporative cooler. Okay, so let me read my notes here, and then I've probably already said most of this, but southwest portion of the country, conditions are often hot, very dry during the summer. In some cases, evaporative cooling can be used to cool and humidify the outside airstream, which then conditions the space. Warm, dry outside air is blown through an adiabatic spray chamber. Well, that's the fancy engineering term. So basically it's an insulated cabinet, and you've got you could spray, you could have nozzles that atomize water vapor, and you could blow it up in there. But of course, you got to be sure, you want to be sure everything gets evaporated, because you don't want to be blowing liquid droplets out of your diffusers. So usually there's some sort of a membrane in there. But so the air goes through this adiabatic spray chamber where it's cooled and humidified. The energy balance on the spray chamber shows that the enthalpies in and out are the same. So it's a constant enthalpy device. So the process line on a Psych chart is one of constant enthalpy. Now, folks, you need to know that. That's probably the most important thing, other than just understanding in general what evaporative coolers or swamp coolers are all about. You need to know how to draw the process line on a Psych chart. It's a line of constant enthalpy. And that's not very hard, but it's hard if you can't remember it. So remember it. Write it down. I don't know. Do something. In a cooling problem for a space, the evaporative cooling process line terminates at the space condition line, giving the amount of outside air needed to satisfy the load. Okay, so you can read that over again. Let's look at a diagram here. Get some pictures. Pictures always help. So let me make it a little bit bigger. So there is our adiabatic spray chamber, i.e. a swamp cooler. So we're coming in at 0, which is the whatever you got outside. You just outside air is being, and there's got to be a fan. You know, come on, man. I didn't draw the diagram, but that air is not going to move by itself. So we got to have a fan in there someplace, which he's not showing. But anyway, so we got a fan sucking in outside air into this adiabatic spray chamber. And it's got nozzles, or it's got a membrane, or somehow the air goes across that wet membrane. And basically we get evaporation, you know, hopefully close to saturation coming out. You know, just depends on the specs on the unit and how good it is. But anyway, we're going to pick up moisture, and that evaporation process will cool the air down. So the dry bulb temperature will drop, but the moisture level will go up until we get to 1. And then hopefully, if 1 is on the condition line, and we've run our loads and all that stuff, then bingo, all we got to do is blow in the right amount of air, and we handle our air conditioning load, both sensible and latent, and we keep the space comfortable, and we didn't have to run a compressor or all that, the stuff that goes with a regular refrigeration system. So swamp coolers are pretty cool, no pun intended. Now let's go down to the Psych chart. There you go. So, you know, we got our loads. We went to the protractor. Does he show? I don't think he shows a protractor on this. Does he? Nah, he didn't put the protractor up here. But anyway, you know, we had our loads. We calculated our sensible heat factor. We went to the protractor. We got the slope. We came down here, and 2 is the condition that we're maintaining in the space. And so it's a air conditioning. So we drew our condition line with the slope from the protractor all the way down here someplace, okay? And then here's our outside air condition, you know, whatever it is, it could change. But anyway, so you put a dot on the Psych chart. I have unstable internet. I just love this place. We still can't have good internet. I think you guys should start complaining about all the tuition you pay, and you can't even have stable internet. You know, we can put grass all over the dadgum place. We spend more money on mulch and grass than we do on instructors, I think. It's ridiculous. I mean, it's nice to have a pretty campus, but I'd rather have stable internet and good teachers than green grass. And if I was you guys, I would raise holy hell about that. And yes, I've recorded that, and I will post it. Okay, so this is our outside air condition. And so this is just a line of constant enthalpy. So whatever that enthalpy is, you find a line of constant enthalpy, and you draw that line all the way off the page, as far as you want to go. Make a line on the desk, I don't care. And if these two cross, then that's going to be the condition of the air that you want coming out of the evaporative cooler, because it's on the condition line. So it has the right amount of moisture and the right degree of coolness in order to offset your latent and sensible loads. So There you go. Pretty simple. Okay, I don't know. If I have any questions on that, there's a good chance this may come. I mean, I like to put these things on test, you know, because if you know what you're doing, it's just unbelievably simple and it doesn't take much time. And if you don't know what you're doing, that's what I'm trying to figure out. So anyway, we'll see. All right. Okay, so this really ends our discussion of psychometrics. So does anybody have any questions on psychometrics? And, you know, I don't know, it's been 2.5 weeks. I don't know, it's been a while. We've been talking about this, but it's really critical that you have a good grasp of psychometrics if you're gonna ever do anything in the HVAC industry. Comments, questions, anybody? Okay, so a week from today, that second psych homework is due. And so about a week from today, I'll email out solutions so you can look and see what you did versus what I consider to be the correct solution. Okay, let's see. So let's go to the Desiccant presentation here. And you guys have this. This is the last email that you got from me because I had forgotten about this. Okay. So a desiccant is a material that has a great affinity for water vapor molecules. You know, we're thinking about doing dehumidification from an airstream. So, you know, this moist air we consider to be dry air, which is what? Mostly nitrogen, oxygen, a little bit of argon, and an ever-growing amount of CO2, right? Okay. And then, so we lump that all together into dry air, and then we have water vapor. Okay, so a desiccant is a solid material. Well, there are liquid desiccants, but in general in HVAC, we usually use solid desiccants that you can like put on a wheel or something that you can force air across. And the water vapor molecules basically stick to the desiccant. So in terms of grabbing molecules, there's absorption, or an absorption, and adsorption, adsorption. So this is adsorbed. And what that means is that there's not a chemical reaction or anything, you know, that basically these desiccant materials have lots of little micro and nano scale cracks and crevices and all this kind of porous and all that stuff. And those water vapor molecules just stick to the surface. And well, so there's a bunch of sites, but there's a finite number of sites in a given mass of desiccant. And so when those all pretty much get filled up with water vapor molecules sticking to them, then the desiccant's saturated and we have to regenerate it. Okay, and so then there's different classes of desiccants that require different temperatures and all of the airstream that regenerates it. By regenerate, I mean, you say you blow hot air across it, that's, you know, if you heat it up, the relative humidity goes way down, and then that dry air basically pulls all those water vapor molecules off of the desiccant, and then it's ready to go again. So you regenerate it, you know, you put moist air, you grab water vapor out of it, and then you regenerate it. So it's a constant process of, you know, dehumidifying an airstream and then regenerating the desiccant, dehumidifying the airstream, regenerating the desiccant. So this gets done with wheels. So you've got a wheel that has this desiccant material painted or somehow affixed to the metal of the wheel. And you got lots of little chambers and passages, and, you know, it's like corrugated, and they put it on there and they wind it all up. And so you've got an air passage through that with lots of surface area for the desiccant to be on. And so then that just rotates between these two airstreams. One is being dried and the other is drying the desiccant. So, and that wheel just rotates around in a circle. So part of the desiccant's always being regenerated and the other rest of the desiccant's always drying the air that comes in. So kind of in a nutshell, that's what we're going to be talking about here. Now, these slides are taken from a Train Engineers newsletter, which if I think about it, I'll send the whole newsletter out to you. There's always more information than you can, you know, than you probably want to put in a, you know, a college course in those engineers newsletters, but I'll be glad to send it to you. So I've just cut and pasted some figures out of that, and then we'll, which is enough to get you the fundamentals, which is what you need to know at this point in your careers. Okay, so desiccant materials, and you know that says ab, and that should say adsorb. I'm going to change that right now. Y'all change this. This was actually done by a student of mine a long time ago, and I didn't catch that. So it's adsorption. There you go. See, I've read this thing several times and didn't catch it. Oh, come on now. Just a little whoop-de-doo. Okay. They adsorb water, oh no. Well, water vapor from the air. I'll fix that other one later. In the HVAC industry, there are three common varieties which are characterized by their ability to hold water vapor at 75 degrees from 0 to 100% relative humidity. Okay, so that's how these things get characterized. And so you see the plot over there. So we got type 1, type 2, and type 3. Type 3 are more recent. They've probably been out there, I don't know, probably 15 years, something like that. But the other two have been out there much longer. So if you look down on the bottom, you've got relative humidity from 0 to 100%. And then you've got just a characterization, low to high, of ability to hold water vapor at 75 degrees. So the temperature is not changing. We're just looking at, because, you know, this is just to give general characteristics. And, you know, 75-degree air, that's just kind of Manila temperature in a space, something like that. So in order to put a curve like this, you got to pick a temperature, and 75 is just what got picked. Okay, so the type 3 down on the bottom, when the relative humidity is low, like, you know, 0, 10, 20, 30, 40, 50, even 60, that desiccant can't hold very much water vapor. But if you put it in an airstream that's like 80 to 100%, it can hold a boatload. That's where it really shines. Okay, and so if you put it in, you know, 90, 95%, it's the highest performing of the desiccants. Okay, because it goes up, you know, over there close to around 100, it's up above the other two. Well, then you see your type 1 desiccants, it holds, you know, a medium amount of moisture over a very large range in relative humidities. Gosh, it probably from what, 40% to 100%, it's pretty much flat. And then you see the type 2, it does from about 60% to 100. It's pretty much at its highest capability, which is pretty good, you know. So say the type 2 are definitely better than type 1. You can tell why it's 1, 2, 3. They keep getting better, except that if you're going to use a type 3, you need to put air that's very high relative humidity across the desiccant so that it will grab a lot of water for you. Okay, so that's what this is looking at. Okay, desiccant dehumidification wheels. Like I said, this is the way those things are commonly put together. And you can see from figure 2, you've got the wheel divided into half. I think really the adsorption part is usually about 65, 70%. But anyway, just for discussion, they divided it in half. And so, so you would have separate ducts. So you would have two ducts sandwiched together, and they're just trying to show the wheel. And so up on top, there would be a duct with dry regeneration air being blown across the upper part of the wheel. And then down on the bottom, there would be a separate duct that was bringing in your process airstream, which is probably outside air that you want to get into the space. And this is like Florida, and the relative humidity is god awful high. And you want to do this with a desiccant instead of just a cooling coil. See, the other way that we get moisture out of an airstream is we just make it really cold. We put it across a really cold cooling coil, and then the moisture condenses out, and then the air might be too cold, and then we have to heat it back up again. So see, there's two energy expenditures. First, you had to make your chill water or your DX system produce very, very cold air to get the moisture wrung out of it. And then you had to somehow heat it back up again so that you don't freeze the poor people in the space. So see, that's what we're kind of comparing and contrasting to here. So this is the other way to do it, kind of like a chemical type process. So the wheels turn slowly, 10 to 30 rotations per hour. The absorption and regeneration processes are driven by the difference in relative humidity of the respective airstreams. And, that goes back to the characteristics of the desiccant. Okay. All right. So traditional. So back for years and years and years, this is how this stuff used to be set up. There's a lot of systems like this still in operation. It's not necessarily what we would do on new equipment today. Okay. And this uses type 1 or type 2 because when these things were put together and installed, they didn't have type 3. Okay. Dedicated regeneration system that includes a heater in order to lower the relative humidity. Okay. So on your regen air, these things were designed to have hot air blown across that coil to regen it. And of course, as you heat it up, then the relative humidity is going to fall like crazy. Okay. So if you look on the Psych chart over here, which shows both processes, let me see, where can I get my marker so it stays visible here. Visible, yeah, now it won't go away. Okay, so this is outside air. This is where both of these are starting. So this is the regeneration air. Well, we start with outside air for regeneration air. And then over here, this is what we're going to use to blow into the space for ventilation. Well, it comes from outside too. Okay, so they're both going to start from the same. It's air coming from outside. It's just we're pulling some for regen, we're pulling some other for actually ventilation air. And it gives you the conditions. And so that's 87 degrees Fahrenheit dry bulb. And look at your humidity. Look at your specific humidity, 130 grains per pound. Remember, we talked about that back in the day. What is there? There's 7,000 grains to a pound. So the Psych chart we've been using has what, pounds of water vapor per pound of dry air. So if you wanted to go back to that Psych chart, you'd have to take 130 and divide by 7,000. And that would give you the correct value to look up on in terms of units of pounds of water vapor per pound of dry air. Okay, so on the regen air, we come in and we go across that heating coil, this H over here. That's just, we're burning natural gas or we got steam or something going in there to heat it. And so we have a sensible heating line, goes off the Psych chart. That's what the ... is. And we wind up here at RG prime, which is 250 degrees. Holy moly. We got to spend some natural gas or something. We got to use some energy to get out there. And say it's the same 130 grains per pound because we haven't changed the moisture. All we did was sensible heating. So y'all know how to do that. And you can calculate the numbers and all that sort of thing. okay? Well, then it goes across the desiccant wheel and it regenerates the desiccant, okay? So in flowing across the wheel, we get to Rg double prime. And so look what happens. The moisture content goes up. It picks up 5, I'm sorry, not 5, I'm looking at the wrong number. 130, gosh, what is that? That's 130, and what is that, 146 grains. It's picking up a bunch of moisture, because that's what it's doing. It's driving the moisture out of the desiccant in the wheel to get it out of there, so then the wheel can move back around and that desiccant can grab some more moisture. So it's a never-ending process as long as you're running the equipment. And notice that it also cools down to 135. So we're dumping a bunch of heat into that desiccant, okay? And so then that air is just discharged back out to the atmosphere, and all that moisture goes back outside through, hopefully a different location. All right, and then so on the process air side, we've got our outside air that comes in, and it's going straight across that desiccant wheel. Well, that desiccant wheel's hot, right? You just blew 250-degree air across it, so it's hot. And the other part of it is there's also heat that's generated when these water vapor molecules are floating around out there in the air. They have some velocity energy and they have vibrational energy inside the molecule. It's an H2O, and those little O's are flopping around on bonds, and go back into your chemistry days and remember all those wonderful tales of molecular energy and how you can have spin, you can have vibrational energy, you can have translational kinetic energy. So anyway, those little molecules have all that energy, and then they go and they stick to that desiccant, while that energy gets dissipated into the desiccant as heat. So just the process of grabbing the molecules causes the desiccant to heat up, and then the desiccant was already heated up because we blew 250-degree air across it. So, you see that when we go from OA, which is just outside air, to OA prime across the desiccant wheel, well, guess what? We get dry because we're going from 130 down to what, 64 grains. So we are pulling a bunch of moisture out, but we're also creating 145-degree air, and you probably don't want to blow that directly into space. Somebody's going to object pretty quick. So then we have to add a cooling coil that does sensible cooling. We're not condensing anything out. That air, that's far too hot. We're way far from the dew point. And so we're just going to do sensible cooling down to our desired 77 dry bulb and 64 grains per pound. He gives the dew point is 55 Fahrenheit. Okay, so what they're doing here is this is just kind of neutral air. So this air is not providing the conditioning on the space. It's just providing the ventilation air, okay, that's required by the codes. Now, a lot of buildings require 100%. So it could be that this is all of the ventilation air, and we have a whole nother system that takes return air and conditions the space and does all of that stuff. Okay, but that's the way this example is set up right now. Okay, so under the tag there on figure 4, it says performance example, desiccant dehumidification wheel. And the location of the wheel is upstream of the cooling coil, because we're going to have several configurations that we're going to talk about here. So this is upstream of the cooling coil, parallel regeneration, which means I have a separate regeneration system in order to make this work. Okay, I think that's pretty much that slide. Okay, well, let's look at traditional arrangement problems. So what are issues that come up with the operation of this? Well, first thing, heater requires additional energy and adds considerable sensible load on the system. Absolutely. So I got to pay money to get from what, 87 dry bulb to 250. And then that wheel is hot. And so that then means my outside air, when it goes across it and gets dried, is 145 degrees. And then I got to turn around and cool that back down. So, you know, that's not great either. Okay, bullet point 2 up there, conditioned air is usually neutral or even warm, which means that we have to cool it down from 145. A cooling coil is more effective when wet. Okay, so cooling coils do a better job operating when they're actually condensing water vapor. And so this poor cooling coil doesn't have a chance because it's seeing 145-degree air coming into it. Okay, and desiccants, and again, that's adsorb. That should be adsorb. So change that on your slide. Adsorb more vapor at lower temperatures and higher relative humidities. Well, see, you know, when you put that outside air across that coil, it's going across. It's not the highest relative humidity. I mean, it's got some for sure. And also it's fairly warm in temperature. It's 87. It would be better if it was cooler and had more relative humidity. The coil would work better. Okay. So those are the comments on our traditional system. Okay. All right, so let's change things around a little bit. So this is called wheel downstream of cooling coil. So moving the cooling coil downstream helps address some of the previously mentioned efficiency issues while maintaining the same dew point. Okay, so we still have parallel regeneration. So let's look. So we're starting at the same point right here. So we got regeneration air and outside, and our ventilation air is both outside air. So the regen now is going across a heater still, but it's only heating to 114. Wow, that's a big difference. And previously we were heating to what, 250. Okay, and then we go across the coil and we exit at 139 grains per pound. So now this one is only picking up 9 grains per pound, and the air exits at 106. So this is much more benign in terms of temperatures swings on the regeneration air. Okay, so then on our outside air, we come in, we go directly across the cooling coil. Okay, so think about it. When you come off of that cooling coil, you're going to be what? Cool, which we want, which helps the desiccant. And the relative humidity is going to be between 90 and 95% typically, which is going to help the desiccant. So this is a really good idea. Let's just do the cooling coil before, and now we're coming off here at 62 and 80. So see, we've already, the cooling coil took us from 130 grains per pound down to 80. What is that? So the coil took out 50 grains per pound, okay, by condensing it. So we obviously have a wet coil, which helps that situation. So this is a better arrangement. And then we go across the desiccant wheel. And now this desiccant wheel it's not as hot because we only put 114-degree regen air. And now I've got 62-degree air blowing across here. So this cold air is going to drastically cool this wheel down, which then keeps it from building as much temperature, which helps us all the way around. Okay, so then we see this is the process line. We come down, and so we wind up at our 77 and 64. So we are going to heat up some because we're going across a coil that got heated up here with 114-degree air coming into it. And then just those water vapor molecules sticking to the surface add energy to the desiccant as well. And so we wind up there. So that's what this system looks like. So desiccant dehumidification wheel, downstream cooling coil, parallel regen. Okay. So everybody jump in if you got questions. Otherwise, I just keep rolling. Okay, now here's kind of the latest greatest. This is going to use type 3 desiccants, and this is called series regen. So we get rid of the separate regeneration system. Removes the separate regeneration airstream, eliminates the need for a heater, so no heater. The difference in relative humidity is driven completely by the cooling coil, utilizes type 3 desiccants, and conditioned air is capable of cooling. Because now this system is going to provide air of much lower temperature, which will handle part of the space loads. That's going to help us. Okay, so this is pretty good. Okay, so we only have the one airstream. So when I look over here at the good old Psych chart, so my outside air is the same as it's been, 87, 130 grains per pound. And so I'm going to immediately go across and regen the wheel. Okay, so when I come out of the wheel, I'm going to be 81 and 137 grains. Okay, so this airstream is going to cool down, what, 6 degrees, and it's going to pick up 7 grains per pound of moisture. Okay, so that gets me to OA prime. And then I'm going to come down and I'm going to go across the cooling coil. So from OA prime to CA is the cooling process across the coil. So I go in at 81, I'm coming out at 58, and my moisture is dropping precipitously from 137 to 71 grains. Okay, and then I go across the desiccant wheel, the process side of it, where I get my dehumidification. And I'm going to increase from 58. So I get what? I pick up 6 degrees in temperature, and I'm dropping, what is that, 7 grains from 71 to 65. And I'm coming in my space at 64 degrees, which probably is not enough to do the whole cooling load, but it'll help because I can put that in and, 64, if you're trying to maintain a 72 degree space or something, 64 helps for sure. Okay. So this is desiccant dehumidification wheel downstream cooling coil series regeneration. Dedicated, and this is a dedicated outdoor air application that we're showing here. Okay, so here's some comparisons between parallel and series. So let's just look. Dedicated outdoor air unit, supply air dew point in the space, both 55. So no change. Supply air dry bulb temperature, so that older, parallel regen was putting 77 degree air in the space, and this series is putting 64 degree air in the space. So that's 13 degree colder. So then they show the cooling capacity of that airstream, and I'm not sure exactly how they're calculating that, but they don't really talk about it. But so they're giving this parallel configuration 8.6 tons, but because the series is colder, it's worth 10.7 tons. So the leaving coil temperature is 62 on the parallel and 58 on the series. Regeneration heat, that's a big one, right? 100,000 BTUs an hour on the parallel and 0 on the series. That's pretty nice. So then the local system cooling capacity on the parallel had to be 15 tons, On the series, because we've got additional air conditioning value in our ventilation air, it only has to be 12.9 tons. So the supply airflow on that interior system goes from 6,000 to 5,200. So there's fan energy savings there. And the total cooling capacity is the same on both systems. So that gives you a pretty good comparison of kind of the old way of doing business versus the new way with the type 3 desiccants. Okay, look at this one. These psych charts just keep getting better and better. You know, maybe we get a few more lines on there. I certainly hope so. Okay, series regeneration, and this is with mixed air. So this is showing, you know, a lot of systems, you know, like in a typical building, you might be 20 or 30% outside air and the rest is return air. You mix them together, and then that's what you have to work on. And so this might be a situation where it's really humid, or maybe you had 30 or 40% outside air. Maybe it's a theater, something like that. Where you have a lot of people, so you have to have a lot of ventilation air. And so you could actually buy rooftop units and DX packaged equipment that have these desiccant wheels built into them. You just specify it as an option. And at the factory, when they build the unit, they go ahead and make it part of the construction. So use the return air and possibly a reheat coil. Allows even lower dew point to be reached, but I mean, that's just an option. So I'm not gonna worry about that right now. Okay, so let's look. So over here, we've got our outside air coming in. We got return air coming back, ducted back from our space. And so guess what? We got a mixing problem, right? And so down here, we're showing return air. And over here, we're showing outside air. And guess what? We draw a line between the 2 points, and then we do our mixing. And so this is showing, let's see, this side represents the outside air. So it looks like it's about maybe 40, 45% outside and about 50, 55, or what, 60, 65% or whatever, the rest of it outside. Because this line, it looks like a little bit longer than this line, and this line indicates the fraction of the return air. So, but it's not too far from 50-50. So anyway, we do our mixing. Okay, and now this preheat coil is not active on the Psych chart, so you know you could put one there just to make sure if it was really cold in the wintertime, you can boost that temperature a little bit. You don't want to get, you know, super cold air into that wheel. But most of the time in the summer, it's not going to be active. Okay, so then we go across the desiccant wheel. And so we go from MA to MA prime, which takes us just from here to here. And what? So we're picking up 12 grains, and we're decreasing temperature by 6 degrees by going across that desiccant wheel. And that's the regen side. Okay, so that's where we're regenerating. So see, all that moisture is going into the airstream, and basically, well, it puts it in the airstream, and then the cooling coil knocks out a bunch of it, and then the desiccant trims it up again before it goes into the space. Kind of interesting, and that was true. I should have said that over here on this one. But see, all this moisture that's taken out on regen stays in the system, and it comes down and hits this cooling coil. And so that's why one reason that cooling coil is colder, so we can condense that out, and then we just trim it down a little bit more with the desiccant coil, the moisture level. Okay, so once we get to that point, then we go across the cooling coil down to CA, and we're showing this at 51 dry bulb and 52 grains with a 49 dew point. And then we go across the desiccant wheel, come down, and we are now 56 dry bulb and 40 grains. So we're losing, looks like 9 grains. And then that's the condition that we're going into the space at. Okay. Now, if we had a conventional system, they've also shown that here. Because see, this conventional system, what we do, we just mix our air and then we go across the cooling coil. And so mixed air go across the cooling coil, we go all the way down here to like 45 degrees. And see, we have to go that low. That's cold air coming off a cooling coil. But say to get the moisture level down, we have to go to 45 degrees. And then guess what? We got to reheat. So then we would go across a heating coil to heat it back up again to get to this same point, because that's the point that we want to go into the space. So that kind of compares and contrasts just the traditional way with this desiccant wheel approach. Okay, then there's also a beast called a total energy or enthalpy wheel. And it's close to the same thing. The rotational speeds change, and it's got a little bit of a different purpose. So the total energy wheel preconditions outside air entering a dehumidifying series desiccant wheel. So the idea here is we're going to precondition this outside air a little bit with this total enthalpy wheel. Okay, so most basically, and that's not my English, but anyway, enthalpy wheels work under the same principle as desiccant wheels, but are used to transfer sensible as well as latent heat. So exhaust air can be used to lower the relative humidity of outside air and heat it slightly. Okay, so it's just an opportunity to do some preconditioning on that outside air, which helps your desiccant system a little bit. This can be very useful for preconditioning outside air before it reaches the desiccant wheel. Sometimes the energy savings are drastic enough that it could warrant downsizing heating, cooling equipment. And we don't have a lot in the way of examples on that here. Okay, so final thoughts. That's just a pretty picture of, that's one of the old parallel systems, but I thought it was kind of pretty, so I put it on there. Whether it will be for dedicated outside air systems or mixed air systems, if dehumidification is a priority, desiccant wheels can often be used to great effect in place of increasing mechanical cooling. So anyway, after hearing this and maybe going over it a little bit, you should have some sort of an appreciation for this desiccant approach to dehumidifying an airstream. And that's kind of what we're looking for here. Okay, questions or comments on this? Hearing none. Okay, so let's see. Okay, I know what we're going to do. We just have lots of different topics here. All right, we're going to talk about, for the rest of the hour probably, VRF systems. And if I had you all in the classroom, I'd want to know if anybody had ever heard of a VRF system. VRF stands for variable refrigerant flow. And these things have been used extensively in Europe and Japan for a long time. They've been fairly slow coming to the US. I don't know if you've ever been in maybe a motel or something that instead of having the three-wall unit had like a unit, a blower unit up on the wall that had a remote control that went to it. Well, that's a VRF system, okay? And these things, compared to a traditional HVAC system, are much more efficient, typically. You can save someplace probably between 15 to 40% of the energy. And so, and this is the new coming thing in HVAC in the States. Just a second, I swear, I have to send my daughter a text. I have to send my daughter the Amazon passcode so she can spend money. Sorry. Okay, I'm back. All righty. So VRF stands for Variable Refrigerant Flow. Well, I just stuck the HVAC systems on there. Okay, so I've got quite a few slides here. Oh, and I sent a link. So this presentation was taken from the train video link that I sent you. I sent you the link to watch. Now, it's about an hour and 20 minutes or something. And so about the first 28, 29 minutes is what's covered in this presentation. And then it goes off on all kinds of things because it's a very detailed. So, I think it would be really good if you watched all of it, but certainly I pretty much covered the first, I think it's 28 minutes. And so I went through painstakingly and I would listen to their discussion and then I would do screen captures of their figures and put this thing together from it. So yes, I have stolen this shamelessly from Train and I give them all of the credit in the world for it. Okay, so a VRF system is a direct expansion air conditioning system that connects multiple indoor units to the same refrigerant system. Okay, so direct expansion, that's what our DX system. That means that the refrigerant is the only heat transfer fluid involved, okay? We don't have chill water or something that we're cooling down and circulating the chill water. We're actually circulating the refrigerant, be it hot refrigerant or cold refrigerant, whatever, to the different indoor units to make this thing work, okay? And so we'll see that we can have one outside unit and multiple. And so well, we'll see as we go through the slides here. Okay, indoor units are usually either in or very close to the spaces they are intended to condition. So there's little ductwork or none at all. And so this is one of the main energy savers, is because these things don't have large horsepower supply fans and extensive duct systems where they're blowing all of this air, a fairly long distance that they have to impart a high static pressure to get it to flow through the ducts and across the cooling coils and all. So, I mean, you still have to force the air across the cooling coils or the heating coils, but the amount of fan energy is just going to be drastically less. Okay. So that's something to note for sure. There are cooling only systems, probably not in this part of the country, but there are parts of the world that are so warm that they just don't have to worry about heating. Heat pump systems, and they can provide heating and or cooling, and heat recovery systems that can provide simultaneous heating and cooling on the same outdoor unit. So you could have 6 indoor units and have 3 of them heating and 3 of them cooling. But see, that's all, these are all slight variations in types of VFR systems. Okay, system components. So we have an outdoor unit. We have what's called a heat recovery control unit. We have indoor units, controls, and refrigerant piping. And that's a picture of an outdoor unit sitting there. Okay, so outdoor units typically contain 1 or more compressors, typically more than 1, because there are multiple indoor units with varying loads. Most units today contain multiple compressors, with at least 1 being variable speed, a variable speed unit for capacity control. So they'll have a VFD on at least 1 of the compressors, because that's the most efficient way you can modulate the capacity of that compressor. So if you just need 1, you would run the VFD. If you need 2 compressors, you would run 1 constant speed and the VFD. If you need 3 compressors, you would run 2 constant speed and the VFD, where the VFD is the one that's always adjusting its capacity to just balance out the amount of heating or cooling that the system needs. The name variable refrigerant flow refers to this ability to vary the amount of refrigerant that flows through the system. Outdoor unit also contains a heat exchanger that serves as a condenser in the cooling mode. So just remember your refrigeration system. You come out of your compressor, if you're making air conditioning, cooling, and you go through a condenser, you condense it at high pressure, you go through an expansion valve, you get mostly cold liquid, and you put that into an evaporator and you evaporate it, and you get air conditioning. So this outdoor unit has this heat exchanger, and it's the condenser in cooling mode, or it could turn into an evaporator in heating mode. And there's also a heat rejection fan. So it's, you know, in that respect, it's like a heat pump. An additional heat exchanger or intercooler is provided to increase subcooling in the cooling mode and heating in the heating mode. So that's for efficiency enhancement. Heat rejection fans. So if you're in a cooling mode, you've got, you know, that coil outside is being a condenser, and you're going to blow outside air across it and reject heat to the atmosphere. So heat rejection fans may be fixed speed, variable speed, or staged. So it depends how much you want to spend. You know, your variable speed are going to be best. If you have 1 fixed speed fan, it's just going to click on and off, and you could have 4 or 5 fixed speed fans that run a different number as the capacity changes. An expansion device is provided to lower the refrigerant pressure before the outdoor coil when operating in heating mode, because in heating mode, that outdoor air coil is the evaporator. And so we got to get that refrigerant really, really cold so it can absorb energy from the outside air. And oil separators installed downstream of the compressor to reduce the amount of oil leaving the outdoor unit, allowing the unit to run at very low loads and accommodate very long refrigerant line runs. These things can have hundreds of feet of distance between some of these units. And when you get into this video, if I have it all in here or not, but they give elevation distances and horizontal distances and all that sort of thing that the designer would need to know when laying out a system. Okay, operation. There's a picture. So you see an outdoor unit, separation tubes. We've got, looks like 3 indoor units heating and 3 indoor units cooling, your refrigerant piping, refrigerant branch control units, all that sort of thing. Okay, let's see what it says here. During cooling operation, hot high pressure refrigerant compressed at the outdoor unit goes to the heat exchanger, which serves as a condenser rejecting heat. Liquid refrigerant is then distributed to the indoor expansion devices and evaporators to remove heat from the spaces. So we're just gonna pipe that cold liquid refrigerant to each one of the indoor units where it has an expansion device. And then, well, it becomes cold after it drops pressure, so it may be distributed. It's probably distributed just after it condenses, so it's still fairly warm. But then when it goes through the expansion device, it gets cold with a little bit of vapor formed, and then you're ready to put it into the heat exchanger, which would act as an evaporator, which would provide cooling for the spaces. Okay, during heating operation, heat pump VRF systems reverse their cycle and refrigerant flow to provide heating. Here, the hot, high pressure refrigerant goes to the indoor units to provide heat to the space and condenses. So in heat pump mode, when you're heating, then, you come out of that compressor with hot, high pressure gas, and that gas is sent inside to your units requiring heat, and it actually condenses inside the indoor coil, and that's where the heat comes from. And so once it's condensed, then it is moved back to the outdoor unit. Refrigerant then flows to the outdoor unit through an expansion device and through the outdoor coil. In this mode, the heat exchanger in the outdoor unit serves as the evaporator. Okay. So it's kind of typical. It's just you have multiple indoor units from what we had talked about before on heat pump operation. Heat pump VRF systems can provide either cooling or heating, but not both at the same time. That sounds inconvenient. Because, what if you're conditioning 6 offices with a VRF heat pump system, and you get 2 people that want air conditioning and 4 people that want heat? Guess what? Somebody's going to be unhappy because they can't, it's either heating or it's air conditioning. So if one space receives cooling, then all spaces will receive cooling. If one space receives heat, then all spaces will be supplied heat. Heat pump VRF systems cannot provide both heat and cooling at the same time. Heat recovery VRF systems have the ability to provide simultaneous heating and cooling because both hot, high pressure gas and cold liquid refrigerant are available to the indoor units. So if you want to be able to simultaneously heat and cool, guess what? You got to go with the heat recovery system, which of course is going to cost a little bit more. Okay, the heat recovery control module, HRCM, enables the system to provide both heating and cooling simultaneously. The control module acts like traffic police in that it is able to direct either hot gas or cold liquid refrigerant to the individual indoor units. This requires sophisticated controls that are able to determine and route the proper refrigerant stream to the indoor units. So this is where the real sophistication of the system comes in. And if you're going to apply this in any sort of a commercial building, this is what you're going to have. You've got to give people the flexibility. Okay, the heat recovery control module is connected to the outdoor unit, and a series of refrigerant lines is run to each indoor unit. The HRCM allows some units to heat and others to cool at the same time. Okay, so you've got to be able to supply what? Hot gas to an indoor unit if it needs heat, or you need to be able to supply liquid that then it'll put through an expansion valve that's going to get cold and so then that indoor coil would be the evaporator and would provide air conditioning. And then you have to have a return line to get the refrigerant back to the outdoor unit so it can be recycled. The HRCM is able to route cold liquid refrigerant to the indoor units needing cooling while sending hot gas to the units needing heating. The HRCM can also route, now this is cool. So the HRCM can also route refrigerant from one indoor unit to another unit directly, bypassing the outdoor unit. So if you've got 2 zones that are sitting there about the same capacities, one is requiring cooling and the other is requiring heating, you can pass refrigerant directly between those zones and avoid going back to the outdoor unit and having it compressed again. So that's pretty slick. So that's where additional efficiency enhancements come into play with this. It's kind of like that water source heat pump loop where we had a water loop circulating. It's really the same concept. It's just we're dumping it into the refrigerant instead of dumping it into a water loop. But then you've got, all the chemistry, the the pressure, the thermodynamic changes in the refrigerant that have to be accounted for here to make this work properly. So this works by transferring energy between indoor units that are working in opposing modes. Okay, indoor units, and we'll have more on this module here in a minute. There are many styles of indoor units that can be selected for a specific application. They usually range in capacity from several. MBH is thousands of BTUs per hour to a couple of tons. Remember, 1 ton is 12,000 BTUs an hour. Each has a fan or multiple fans. It may be constant speed, step, or variable speed. Each contains a coil and expansion valve for cooling mode. Some models are designed to fit into a small closet or above a drop ceiling and discharge directly into the occupied space. Other units require small sections of duct to discharge air into spaces. So like these guys on the bottom, this would go, say, above a drop ceiling or maybe in some sort of a closet or something, and then you'd have to run a little bit of duct work to get to some diffusers to distribute the air. These cassettes set in the drop ceiling, and these guys just set high on the wall. This is what you see sometimes in the motel rooms and that sort of thing. Controls are key to a VRF system. It includes zone level, system level, and building level control and proper integration to ensure good operation. At the zone level, a wired or wireless control unit allows individual space temperature control. This is like almost like a remote control on your TV. And yeah, I mean, it can be wired, but I think they're typically not at this level. Piping, each unit in the system, indoor unit, outdoor unit, and heat recovery control module are also connected by a series of refrigerant lines. Depending on the number of indoor and outdoor units, the quantity, length, and lifts of these lines can be thousands of feet. This allows outdoor units to be placed a significant distance from indoor units or even on the roof of multi-story buildings. So you can get significant lifts. So you put those on the roof and you can run those refrigerant lines down to the individual units. System operation, outdoor units. As we said, there are 3 basic types of outdoor units. The smallest units are mini VRF, and these are available only as heat pumps. They are 5 tons and under. Single phase power, which is typically for residential type applications, limited number of indoor units, and cannot be combined to form larger capacity outdoor systems. So this would be like for a house, something like that. If you had more than 5-ton load, you just have to have 2 systems. Of course, if you had 2 systems, then one could be in their basically their heat pumps. So one system could be in heat and the other could be in cooling, but you can't get the simultaneous heating and cooling in these small ones. For conventional systems, most common model is an air-cooled unit. So these are larger, offered with 3-phase power for any sort of a commercial type application. We'll have 1 or 2 upflow condenser fans, modular, with units offered in distinct capacity increments, often 7 through 14 tons. Individual unit modules that should say can be combined into groups of up to 3. So you can get them up to about 36 tons if you group them together. Buildings larger than 36 tons just require more than 1 VRF system. So, you can put in multiple systems. So if you had a 100-ton total load on the building, you'd wind up with 3 VRF systems and you'd have to divide it up. Okay. Outdoor units are also available for water-cooled applications. So they have, instead of air-cooled condensers, they have water-cooled condensers. You then would have to have a cooling tower, some sort of a cool water source to make that operate. Similar to air-cooled models in terms of voltage, tonnage, and modularity. Primary difference is the outdoor unit uses water instead of air to exchange energy with the environment. Can be installed either with a ground loop heat exchanger or boiler and cooling tower, and can be installed either inside or outside. There's a little picture. Okay, indoor units. I tell you, I think that's enough. I was kind of hoping to get through this today, but I don't want to pound you too much on one day. So let's go ahead and cap this off here, and we'll come back and finish this next time. And then we're going to move into some more hydronic stuff. That PowerPoint I sent on air control and hydronic system will be our next target after we get through the VRF systems here. So hope everybody has a great day and enjoy all this good stuff. And we'll be back together next week. Hope you have a good weekend as well.